So this first question is an application question for the Pythagorean theorem. It says to meet safety requirements, a wheelchair ramp must have no more than 1 unit of rise for every 12 units of length. Does the ramp shown meet the requirements? And we can see that we have this right triangle representing our ramp, where we know one leg of the right triangle, and we know this side of the right triangle. So we can, I think, pretty easily find this side of the right triangle. Let's start there, and then we'll see what the answer to our question is. So we're going to start off using our Pythagorean theorem, a squared plus b squared equals c squared. And this missing side I'm going to call b. So that would mean that this is going to be a, and that is going to be c, because we always know that c is going to be the hypotenuse, which is the side that's across from the right angle. So we're going to have 41 squared plus the missing side squared equals 500 squared. And then if I simplify, I have 1,681 plus b squared equals 250,000. And then I'm going to subtract 1,681 from both sides. B squared is going to give me then 248,319. So b would be the square root of this 248,319, which is going to be about 498.3 centimeters. So this ramp has these dimensions. We got a rise of 41 centimeters and a length of 498.3 centimeters. So now I just need to think, does this ramp meet the requirements? And so the requirements say that if I make a ratio of rise over length, it should be, it should be 1 over 12, or basically this number on top can't be more than 1 when I make the numerator or the denominator a 12, right? It can have no more than 1 unit of rise. So this number on top would need to be smaller than 1 if the denominator turns into 12. So let's think about the ratio that we currently have in our picture. We have 41 centimeters over 498.3 centimeters. Well, if I turn that into a denominator of 12, what does this numerator become? And I think I can solve this by cross multiplying, right? I can take the 41 times the 12 equals the 498.3 times, we'll just say x for this unknown amount up there. And then 41 times 12 gives me 492 equals 498.3 times x. I'm just going to recopy this up here. 492 equals 498.3x. And then I'm going to divide both sides by 498.3. And now I have 492 divided by 498.3. And that's going to give me 0.987 for the approximate value of x. So what does this tell me? It tells me that when I make the actual ratio of rise over length for my picture, for my ramp, into a fraction with the denominator of 12, this numerator becomes something less than 1. So it doesn't have more than 1 unit of rise for the 12 units of length. It has less than that. So I think our ramp is good. So we will say yes, the ramp meets the requirements. And there we have our answer. So then our next question says, is this triangle a right triangle, and explain. Well, we know that if it is a right triangle, then a squared plus b squared will equal c squared. So what we're going to check is, does that happen in this picture right here? Do the two shorter sides, when I square them and add them together, equal the longest side when it gets squared? So I'm going to say that the 12 will be the a, 12 squared, the 35 will be the b, so I'm going to square it, and I'm going to ask myself, does that equal the longest side, 37, when I square it? Well, 12 squared is 144, 35 squared is 1,225. Does that equal 37 squared, which is 1,369? Well, 1,225 plus 144 does equal 1,369. So yes, these two sides equal each other, and yes, this is a right triangle. And if you wanted to give a reason, like if you wanted, this is kind of my explanation here. I'm explaining that the side lengths fit into the Pythagorean theorem. So I'm not going to give an additional explanation. This is kind of my explanation right up here. Now my third example shows me this picture and wants to know how long these two sides are. Now what I'm going to notice is that this is one of the special right triangles we talked about. It's a 45, 45, 90 right triangle. So I know that in a 45, 45, 90 right triangle, all the side lengths kind of have this special connection to each other. If the sides across from the 45-degree angles are both 1s, then the side across from the 90-degree angle is a square root 2. And so what I'm going to do is I'm going to set up this proportionality statement that says, hey, this triangle would be similar to a 45, 45, 90 triangle that had these sides, 1, 1, and square root 2. Right? It would be similar to another 45, 45, 90 triangle where these are the side lengths. So now what I'm going to do is I'm going to make the ratios of the corresponding sides based on what I see in this picture. I know that across from one of my 45-degree angles in this picture is segment BC, right? That's across from that 45-degree angle. Across from the other 45-degree angle is segment AC, and then across from the 90-degree angle, I have a side that is 14. So if I look at this picture, what I can now do is I can maybe choose these two ratios that are equal, and I can cross-multiply to solve here. So I'll do that. I'll say AC times the square root of 2 equals 1 times 14. So AC root 2 equals 14. And now to find the value of AC, I need to divide both of these sides by square root 2. So AC is now 14 divided by square root 2. But we can't leave our answer like this because it's breaking one of the rules of math, which is that it has a square root on the bottom. And that's a kind of a no-no in math. We're not allowed to have a denominator with an irrational number, a square root that's not a perfect square root. So I need to what's called rationalize this denominator. And I'm going to do that by multiplying both the top and the bottom of my fraction by the square root of 2. That means the top will turn into 14 root 2, and the bottom will just turn into 2. Because when I take the square root of 2 times the square root of 2, I'm going to get the square root of 4, and the square root of 4 is 2. Then I can simplify the 14 over the 2, and I can say that it's 7 square root 2. But now that's AC. AC is 7 root 2. But I actually know that that's going to be BC as well, because remember 45, 45, 90 right triangles have legs that are both the same length. So this leg right here will also be 7 square root 2. So both AC and BC are 7 square root 2. Here in this final example, we see another one of our special right triangles. This time we're looking at a 30, 60, 90 right triangle. Now I know that that every 30, 60, 90 right triangle will be similar. So this triangle would be similar to any other 30, 60, 90 right triangle. One kind of 30, 60, 90 right triangle would have side lengths where the side across from the 30-degree angle is 1. The side across from the 60-degree angle is the square root of 3, and the side across from the 90-degree angle is 2, twice as big as the side across from 30. So now what I'm going to do is I'm going to again set up these three ratios that should all be equal, where the top numbers are all the side lengths in my kind of hypothetical 30, 60, 90 right triangle, and then the bottom side lengths are going to be what we see in this triangle. So across from the 30-degree angle in this triangle, I see segment BC. Across from the 60-degree angle, I see a side that's 28 units long, and the side that's across from the 90-degree angle, I see segment AB. Now I'm going to pick out two of these ratios and solve for something that's missing. So for instance, I can pick out these two ratios and solve for BC. So that's going to be 28 times 1 equals BC times the square root of 3. I'm going to divide both sides by the square root of 3. So BC equals 28 over square root 3. But I can't leave it like that because I have that irrational number in the denominator again. So I'm going to multiply by the square root of 3 over the square root of 3. And that's going to say BC equals 28 square root 3 over 3. This denominator is going to turn into 3 because the square root 3 times the square root 3 will be the square root of 9, and the square root of 9 is 3. So there's my length for BC. Now I can do two options. I can now realize that, okay, that's the short leg, and the hypotenuse should be just twice as long as that. Or if I don't do that, then maybe what I'll do is I'll set these two ratios equal and cross multiply to solve. So let's go that route. That's going to say that AB times the square root of 3 equals 28 times 2. So AB square root 3 equals 56. And now when I divide both sides by the square root of 3, AB equals 56 over root 3. And so I'm going to rationalize the denominator by multiplying by the square root of 3 over the square root of 3. And AB is now equal to 56 root 3 over 3. So here's my BC answer, and here's my AB answer.